Okay, morning everyone. How's everyone? Tired. You guys had a good weekend? No tests? There's always a test. Do you have a test this weekend? Week? Oh, okay. All right. Shh. Just pretend you have a skills test on Friday so that you can finish your vector studying, hey? Just pretend. Right? The week after is your class test, hey? So please, vectors and all of matrices, so just start preparing for vectors. Do every single question. Then look at past papers, yeah? Okay? So, but you must study notes first, right? Notes, TATs, exercises, homework, whatever, and then past papers. Do all that in that sequence, okay? No spotting. Spotting never helps anyone. All right. We have been doing Gauss reduction, and we've also been interpreting our Gauss reduction. But just to solidify that interpretation, there's some questions on the board. See if you can do them. All right? See if you can do them. Interpret those answers. What do they? So that means I can't do any more Gauss reduction. That's the final Gauss reduction step. Right? Can write here. After no more Gauss reduction can be done. Come on, guys, let's go. Question mark. Yeah? Come on, guys, we're doing those questions. Can you do them? Sorry.
This question. I'm sure that you can work past this because if you assume that this was a constant, how do you know that you should use 0 or 1?
It's by inspection. By inspection. If you factorize that, then it's k squared k 1 minus k. And so if I make k either 0, then that whole line is 0. Or if I make k equal to 1, then we're going to have 0, 0, and a value.
That I get, but is it, if you get something like this, is it, you assume 1 and 0 immediately?
No, you have to look at it. It's by inspection. It could have been k squared minus 3k cubed. And then it won't be, it will be 0 and root 3. Yeah? Something like that. Doesn't matter, as long as you label it. All right? In this one, I'm going to use x1, x2, x3, x4. It's just names. Okay? Okay, guys, come on. Are you done? Are you done? Come on. Let's go. Ooh. All right. Okay, I'm going to label mine, guys, I'm going to label mine x1, x2, x3, x4. If you did W, X, Y, and Z, that's fine. If you did X, Y, and Z, W, that's fine. All right? Depends on what you want to label it. Just make sure it's clearly, right? So X1, X2, X3, and X4 in a column vector. Just what you envision, what you must envision is that there's 2 rows of zeros there. Right? We've got our diagonal, then there's 4 unknowns, so there can be 2 rows of zeros. I don't usually write them down, but that's what you should think about. All right? So if there's 2 rows of zeros, what do you think there should be? Not lambda, we can say 1 is lambda, 1 is mu. Okay? Or S and T, whatever you want to say. All right? So here we write your X1 for your first values without the all right? So this would be minus 3 over 2, 5, 0, and 0. Oopsie, sorry. Right? Now think of this. This would be your lambda. Right? And this would be your mu. All right? But now we're taking it over to across the equal sign. That's your equal sign. We're taking it across there. So this becomes plus a half. Right? I'm not going to write out x1 plus minus x, half of x3 plus 2x4 is equal. I'm not going to write them out. I am interpreting straight away. You can do it if you want to. All right? But we've been doing this last week, so this should be just carrying on. If you're still having to write it out, see if you can do it without writing it out. All right? Because we want to be efficient. Yeah? So this is saying x1 minus half of x3 plus x4 is equal to minus 3 over 2. We take that to the other side, so we can say x1 is equal to something, right? So if we're taking this to the other side, if we're saying let x3, basically saying let x3 equal to lambda and x4 equal to mu. All right? So this x3 minus a half x3 goes onto the other side, becomes plus a half x3. But x3 is equal to lambda, and so it's plus a half lambda. All right? Another question? Come on, say it. We are saying it can be S or T, but remember what I said, there are 2 rows of zeros there, right? So if we're imagining those zeros, right? So we're saying let x3 equal to lambda and x4 equal to mu, all right? We could have said S and T, whichever you want. I like to use lambda and mu. Okay? Question?
How do you know x1 and x2 can't be lambda?
I know why x1 and x2 can be lambda because I've got my diagonal there. That's saying x1 is equal to something. x2 is equal to something. But now I have got no x3. Can you see it? I've got no x3 and x4 because they're rows of zeros. You get it now? Guys weren't revising. Did you do any class reduction this weekend? You were supposed to finish 1, 2, 3, and 4. Questions 1, 2, 3, and 4. And questions in your notes which we painstakingly printed out cost. Right? I think from next year I'm not printing out. Just on Vula. All right. So then x2 is equal to 0 lambda plus mine, right? I'm taking it over that side. But let's just look at the lambda values. And that's why it's going to be 0. The next one, because x3 is lambda, there's a 1 there and a 0 there. If you would prefer, I go across. Let's see what happens. Shh. Guys, if you're not understanding, right, don't talk to each other just yet. Listen to me. All right? You need to be able to keep up. You are not preparing yourself well for next year if you cannot keep up with this simple stuff. You have to have revised in the weekend. This is just normal. It's just normal part of life. Revise in the weekend. Make sure you're up to date. You were supposed to do questions 1, 2, 3, and 4. And in part of them, there were some interpretations. So this shouldn't be that difficult. All right? This is supposed to recap, recontextualize. I want you to please prepare well. In the weekend is not for, I know the weather was so good. Oh, it was really good. And most of you were outdoors. I know that. But take your books next time when you're going outdoors, eh? Sit under a tree. Sit under a tree, eh? Do your work. All right, shh. So x1, let's look at it this way. x1 plus 0x2 minus a half x3 plus x4 is equal to minus 3 over 2. Yes? So if we're saying, what is x1? We're taking everything over to that side, past the equal sign. When you take it past the equal sign, it goes to negative, right? So this is going to be x1 equal to minus 3 over 2 plus a half lambda minus 2 mu. All right? Then this row, x2 is equal to 0 lambda plus mu. Sorry, 5. Sorry, there was a 5 first. 5 plus 0 lambda plus mu. So there's your 1. Then we're saying x3 is just simply lambda. So it's going to be 0 plus lambda plus 0 mu. And x4 is equal to 0 plus 0 lambda plus 1 mu. And that is our writing our answer in your column vectors. All right? And so what, basically, to interpret this, if it was, we can't say it's in 3D, so we can't do a geometric interpretation, but basically this is what we call a linear combination. Okay? Okay, one more time, x3. Just imagine these rows of zeros here, right? And we said x3 is equal to lambda. So if x3 is equal to lambda, it's basically saying 0 plus lambda plus 0 mu. Right? So then it's 0 plus lambda, which is 1, right? There, plus 0 mu. Okay? x4, again, we can say it's 0 plus 0 lambda plus mu, 1 mu. So it's 0 plus 0 lambda plus mu. Okay? All right? The next one, let's do this one. This is a 3 by 3. Yes? Yes, where's the question?
Why don't we just put in x3 and x4 instead of lambda and mu? Because then you have 4 variables instead of 6.
This is just how we interpret it, Because if we said x, if we just say x3, we could. We're not introducing. We are saying what is x1, x2, x3, and x4, and they can be described in terms of those two variables. Because we can't just say x3 is equal to x3. If we had changed this and then said this is x3, it's simply x1, yeah. We just introduce two more variables. It's just the convention. You can't just say x3 is equal to x3. We have to introduce a new lambda, because then we are saying this in terms of a variable, because then we change this value. It can be anything. Lambda and mu are elements of real numbers. And then this is now what we would call a linear combination, where we can get any point, or if it was a 3 by 3, or any value, right? Depending on what lambda and mu is. So it can describe probably, if you're looking at optimizing something, can describe a surface. Right? Question?
Let's say you're doing this, like you break your matrix into parametrics, right? If you wanted to represent x2 and x3 and x4, would I be wrong if I just put x3 is equal to x2 before I let the whole?
No. That's fine. If you're doing it the long way and you're writing out, let x1 equal to minus 3 over 2 plus x3 plus 2x4. If you wrote it out, that's fine. I'm just going to mark there and mark there. Right? Because that's what I'm interested in. Have you interpreted the answer correctly? All right? All right. Shh. This one should be a little bit easier. There's only one row of zeros. Now, if you looked at it, my diagonal lies here. I could actually move this up there and have the diagonal there. That's fine. All right? Either way, but I'm going to choose to leave it like that. All right? So I can interpret this two ways, but in this way I'm going to choose my y equal to lambda. All right? So here we've got x, okay, let's see, x, y, z equal to 703 plus now lambda, and so, oopsie, this was the lambda column, so this is minus 1, 1, and minus 1. That's it. Lambda is an element of R. We could change it. We could swap our rows. And both answers would be correct. If we swapped our rows, what would it look like? 1, 1, 0, 7, sorry. 0, 1, 1. And 3. Here's our diagonal. That's fine. And so we get x, y, z equal to 730 plus mu. And we'd get minus 1. Hi. No, hang on. So now this is your lambda, your mu. So what would happen there? I would actually, if I make this my mu, this needs to be, I need to Gauss reduce this further. So I'd say row 1 minus row 2, and so I'd get that 0 minus 1 and 4. Yes? So that's 4. And I can leave this as is. Right? So then it becomes 4, 3, and 0. And then this is my mu. And so it's, yeah. So that becomes plus. That becomes minus 1. And that becomes 1. All right? If I say, well, I want to keep this, I want to keep that as a 1, right? And if I said that, okay, so I say if I want to make that 0, I can't do anything with this one. Because if I do this, this becomes a 1.
And the M1, the middle.
The middle one?
No, it's the M1. The middle.
This one. If I say that minus that, yes, I could. Yes, I could. I could. So both answers are correct, though. Both answers are correct. So we'd get that. It's the same thing. We'd get that 0 minus 1 and 4, 0, 0, 0 and 3, 0, 1, 1 and 3. So here we'd get 4, 0. Did I write this right? This 0. 403. Yeah, 403. Let's just do this. No, actually, or we can say or x, y, z equal to 403 plus mu, and we can say that's so that's 0 up here, and then that is, have I done this right? Z is equal to 3 minus, yeah, that is 1. Z is equal to 3 minus, there we go. All right? Okay? Both are correct. Question? Oh, because I'm saying if I let my z equal to mu, I've still got something here. So I'd still be saying x plus y plus something. So that's why I want to Gauss reduce here. Here, I said this row, this column is my y. And I can't Gauss reduce this one anymore because there's 2 zeros there. So this one, that's why I couldn't Gauss reduce this one. I could Gauss reduce this one to get rid of that 0, but it really makes no difference. Really makes no difference if I Gauss reduce this. As long as I got my variable row and decided which one is my variable row, and then I let that. So I'm not saying, because then here we're saying x plus lambda is equal to 7. So then we take that lambda over to that side, and so it's 7 minus lambda. All right, so it really is when we want to Gauss reduce, is when we're saying if I let my, whichever one, is this going to be my lambda? No, I'm making this one my lambda. All right? If that's my lambda, then if I'm saying that plus lambda, that's fine. If if this was a 1 here, I'd Gauss reduce it further so that then I don't have to put in another variable. Okay?
Looking at this equation here, how do I interpret it? Is it like, do I say to get to this point, I move from this point using these vectors? Or
Yeah, so basically lambda and mu can be anything. My values, you'd get x1, x2, 3 is equal to lots of points, which would make up a surface. Or we can't interpret it so much geometrically because there's a fourth dimension. So it's like saying apples, pears, bananas, and oranges, rather. This many, so these are my solutions. Okay? If you look here, right, so we've done in our books, we've done section 1, section 2, Gauss reduction, section, so here we go. Please have a look at the system. Now they use fractions, which is fine. If you want to go that route, it's fine. But in the end, we end up with the same values. All right? And then they even say what it looks like geometrically for the 3 by 3. And then we're going to talk about linear combinations just now. All right, shh, guys, what we're going to do now, shh, this wasn't supposed to take long. We're going to do what is a linear combination. So this is basically a linear combination. These are when we make lambda is equal to something. These are linear combinations. So, just want to write something. Linear combination. As I said before, you write your answer in terms of a linear combination. But basically, if we wanted combination, if we wanted a particular value, then your lambda and your mu must be something. Oh, God. Okay, so if we had this combination, 1, 2, 3, lambda times 1, 2, 3, and mu times a half, oh sorry, let's make it 4, 5, and 6, we're just taking anything, equal to 5, 7, and 9. All right? So this is, I don't know if this is even in this book, but basically this is just expanding on the concept of a linear combination. I don't think it's, let's see, I don't think it's written here specifically. No, it's not written specifically, but if you look on page 14, all right? Yeah, if you look on 12, sorry, it's just, I think, 13 disappeared. Where's 13? This is when you give things to people. Oh, okay, sorry. So 13 and 14 are the wrong way around. Please just have a notice. So if we look at 13 and 14, they're talking about linear combinations. And so for specific values of lambda and mu, you'd get a point. By inspection, can you determine what is lambda and mu? Just by inspection. 1 and 1, right? All right? If we made lambda equal to 2, then our point would be different. It would be 6, 6, 9, and something else. What is it? 2, 3, 6, 12. 6, 9, and 12. Okay? So the idea is these things represent, they should be real numbers. All right? And we get, when we talk about linear combinations, we mean if I made lambda equals to this, what would I get? So we get a solution. A solution of, in this case, it would make up a plane maybe, passing through the origin, in fact. It would be making up lots of points. All right? Lots of points. It will make up lots of points. And so we get a solution that can be represented like this. This is what we call a linear combination. I mean, because I mentioned it so briefly, it's just a naming, really. But the idea of this many of something. When we did vectors, remember we talked about we'd get from there and then we on here and we'd say this much of one vector plus this much of another vector to get you to that point. It's the same idea. So this is just the linear combination to get you to that other point. Okay? So if we change lambda and mu, you'd get lots of different points that would probably lie on the same, that do lie on the same plane. Okay?
So is this format called the parametric equation?
Yes. These are parameters. So you can see the relationship between vectors and matrices, right? They're very closely linked.
Then if you change the parameters, you won't get back to
No, you won't. So the next one, if I change the parameter, I'd get another point, right? So if lambda equals to 2 and mu still the same 1, then we get what point? I said just now, what was it? 6, 9, and 12, eh? Yeah, 6 plus 6 is 12, yeah. So we get different points, but they would be lying on the same plane. So this plane actually passes through the origin. We can say it's 0, 0, 0 plus, right? Okay. So right now, make sure you go and do all the exercises. Not right now, but up to this point we have worked. All the exercises up to page 17 for homework tonight. Just, yeah? All right? Shh. You should know where you're up to. Come on, guys. I don't have to tell you that. That's supposed to be logical. Deducing. So guys, I know I harp on about this. I harp on and I want, and my saying things are not going to change habits. I know that. But just for you to think about who of your friends is doing really well, right? And what are their habits? Have they spoken to you about their habits? Do they keep up? And I guarantee you the top students are keeping up, and I know who they are. They are keeping up because they ask me questions all the time. So please, keep up. All right? Keep up so that when you're stuck and you're doing your exercises, you've already encountered that question in your mind and you've done it, right? So please keep up. that means about where we are in our syllabus, right? It doesn't mean, okay. So now what we're going to do is just talk about matrix notation in general. So we were doing augmented matrices, right? With the line in the middle, that's called augmented. Now, if we look at, we're just going to talk very briefly about matrices in general. Okay? Now, you've come across matrices, but how we write notation of a matrix, if we're describing a matrix, you know points, you know vectors. When we say matrices, we give it a capital letter, right? A, B, C, D, X, Y, Z, as long as it's capitals. And then we've got an equal to sign, and we write our matrix out with brackets, okay? So basically it's just a rectangular or even square array of numbers. That's what a matrix is. And they're basically describing an operation that you're doing to something, all right? We'll talk about that more when we do transformations. So your matrix here, if I write it out, I'm just taking some values, 7, 8, 9, right? These are your rows, as you know. Row 1, row 2, row 3. And these are your column 1, column 2, and column 3, right? So when we're describing this one, we say M rows, which in this case is 3, right? Rows, and N, in this case, N is equal to 3 columns. And so when we say it, we say M by N matrix. So when we're talking about this, we say it's a 3 by 3 matrix. So therefore, when I look at another matrix, let's say B, right? Let's give it 1, 2, 3, 4, 5, 6, some values. So this here is again, this is how many rows? 2 rows, right? And it's 3 columns. So this is what we would call a 2 by 3 matrix. This is describing the size. Describing size of matrix. Okay, so when we talk about matrices, this is a 3 by 3 matrix, this is a 2 by 3 matrix. Okay. And basically, all right, so then quickly you can think about, as we're writing, different matrices. So, okay, if I looked at and we call them I's and J's, the columns are I's and the A by, we call it I and J, right? This represents the rows and the columns. So if I looked at the last one, so in B, basically the coefficient of A2, 1, right? A2, 1 is what? If I say I is the number of rows and J is the number of, it's 4, right? Okay, so those are just coefficients. So when we talk about the coefficients, if I want to be specific and talk about the 1, 2 would be 2, right? The first row, second column. Okay, so just how we talk about the things, all right? All right, what else can I say? In general, let's see. In general, this is also a matrix, right? What size is this matrix? 1 by 2. 1 by 2 matrix. All right. And if I wrote it out like this in column vector form, this is a 2 by 1. We can even call it a column. So matrix, but because it looks like a column, one column, we can say column vector. So either we call it a 2 by 1 matrix or a column vector. All right? Just names. Okay? So when we're talking about, now we also have the zero matrix. Just like in zero vector, remember we talked about it? Zero, we have a zero matrix, so the matrix has 0 entries in it. So we can do something with it. Okay? When we say 2 matrices are equal, yeah? Oh, come on, guys. You're supposed to take down. Oh, it's coming. Okay, let's go on this board. So, and a good skill to have, and which some of you have already, is to take down lots of stuff that I say, but don't write down. What I write down is a given. You must take down. It's a must. It's a must. It's a bare minimum. What I say often is more than what I write, and that goes for all your lecturers. All right? What people say is more sometimes than what is written down. So write, interpret, listen, interpret, write down. Okay? And write faster. Write faster. Okay? All right, so we also have a zero matrix, which is like the zero vector, because vectors are really matrices, right? Vectors are just column vectors are matrices. They just, yeah? Whose entries we can say entries or coefficients are zeros. Okay. So the next one we were talking about, what did I say? So if we're looking at matrices that are equal, yes.
Can you draw the matrix that is 0 by 0?
No, you see, a matrix is an operation. It's not, you can't geometrically interpret it. When we talk about, we will do transformations tomorrow or the next day, when we'll talk about what that operation does to a point, if we want to talk about it geometrically. So it's basically an operation. It's like a black box. It's doing something, it's taking an input and giving an output. That's what it is, a matrix when we do something to something. All right? But we only can do it after we talk about general stuff like this. All right? We'll talk about even matrix multiplication if we get some time. All right, so 2 matrices are equal. If and only if their entries are the same. 1, 2, 3, 4. 1, 2, 3, 4. They're only equal if exactly the